Hey everyone, I hope you're doing well. My name is Anj, and I'll be taking you through my final project on MRI brain tumor detection. I am a bioengineering student, so I decided to use the project as a way of fusing together my interests in biology and computer science. To start off with, I'd like to give you a bit of context behind the rationale for my project. Brain tumors are a serious and aggressive form of cancer that can affect both children and adults. They account for a high percentage, 85 to 90% of all primary tumors in the central nervous system. Each year, approximately 11,700 people are diagnosed with a brain tumor. To improve the life expectancy of patients, proper treatment planning and accurate diagnosis are crucial. Magnetic resonance imaging is the most effective method for detecting brain tumors, as it generates large amounts of image data that can be examined by radiologists. However, manually reviewing these images can be challenging due to the complexity and unique characteristics of brain tumors. This is where image processing comes in, as it can save physician time at hospitals while increasing the accuracy of diagnosis. So, the goal of my algorithm was to use image segmentation and processing to essentially dissect an MRI scan, leaving just the tumor behind. During the planning phase of my project, as indicated in my final project proposal, I had the intention of using KNN clustering and machine learning to classify the specific type of tumor. However, during the coding stage, I very quickly found out that I was taking on too big a task and decided to narrow down my project into the field of image processing rather than spreading out. I didn't realize how complex brain tumors were. There are a lot of abnormalities in the sizes and location of the brain tumor. Hence, I couldn't just base my classification on one variable, that being size. There are many different factors such as the location and the age of patient that needs to be taken into account. While coding the program, I had to research many different methods involved in image processing, such as anisotropic diffusion filtering, which basically removes noise from an image. I utilized techniques such as blob analysis and connected components labeling to remove the skull from the MRI image. A blob is anything that is considered a large object or anything bright in a dark background that can be generalized as a group of pixel values that forms a colony distinguishable from its background. Finally, I use highness threshold filtering to deblur the MRI image and add details so that a better tumor dissection could occur. Now I'll take you to the actual MATLAB code and you can see what the final product is. After running the start code, the detection file is executed. As you can see, there are 7 images that are outputted. The user inputs an MRI scan from a folder of over 150 images. The algorithm then increases the amount of detail in the image by adding the high-frequency components. After that, the image undergoes an initial threshold and then separated into distinct blobs to strip the skull. This is necessary to isolate brain tissue from non-brain tissue. A dialog box then pops up for the user to interact with, and they are allowed to find the tumor if they want to. As you can see, a second threshold is applied at a higher grayscale level in order to find the tumor more accurately. The tumor is then shown on its own, as well as with an outline and a red tint on an overlay. Another dialog box pops up in order for the user to find out some more about the tumor, such as its classification. As you can see, the algorithm found that there was a tumor and is given a few statistics such as its area, circularity, diameter, and perimeter. This is useful for radiologists in order to classify it into the specific grade, as well as whether it's benign or malignant. Now I'll take you back to the actual code itself and you can see how this came about. This is the start file, and it basically executes these following files. This is the identification file. The user inputs a file name over here from a pre-selected folder. Um, After that, the image is converted to grayscale. A high-pass filter is added using the following function. After the high pass, a threshold is applied using a normalizing technique, and a binary image is created. After that, a hole fill is pursued in order to remove any background pixels inside a blob. This ensures that there's no weird tumor that is outlined at the end. Connected components labeling is then undertaken in order to distinguish each specific blob, and after that, the skull is masked out of the image. A second threshold is then applied over here in order to specifically isolate the tumor. It is assumed that the tumor is now the largest blob segment and is then masked out on its own. A boundary is then applied in order to outline it, and then a tinted plot is created over here. The transparency of the red overlay image is set to be 30% opaque and 70% transparent. After that, if the user wishes to continue on and classify the tumor, the following file is run, the classification one. I use region props, an inbuilt MATLAB function, in order to get the area, circularity, diameter, and perimeter. The problem what I found was that these were all given in units of pixels, which weren't standardized in the field of biomedical engineering. So therefore, I had to convert these pixel units into more standard units, such as millimeters or centimeters. I decided to use centimeters here. I used the screen size in order to calculate how the resolution of the screen, as well as how much of an area the pixel occupies. The unit conversion occurs over here, and then a dialog box is finally created in order to alert the user about the tumor's information. That's all, and I thank you for taking the time to listen to this.